Hello, for this video I'm going to try to get through the entire acid-base equilibria side of this page with the find someone who. Okay, I'm going to go across 1 through 4, 5 through 8, and so on. Who can define a buffer? A buffer has to have either a weak acid and its conjugate base present in solution, or a weak base and its conjugate acid present in solution, so that it will resist changes in pH. It resists it by either shifting right or left, and that only happens if you have the acid and its conjugate both present. Okay, drawing a titration curve for a strong acid and strong base. It could look either way here. The first example is if we have the acid in the flask and we're adding the base from the Burette, and this would be if we had the base in the flask and we're adding the acid from the Burette. Because they're both strong, it's not obvious which one is in the flask and which one's in the Burette. They should be symmetrical, and the equivalence point on both of these should be at a pH of 7. Because a strong acid or a strong base does not have a conjugate that will do anything in solution. So that's number 2. Okay, who can write a Kb expression? Well, a base in water takes a proton off the water and leaves the hydroxide ion, so that's the base, that's its conjugate acid. There's the liquid water that will not be in this, there's the hydroxide that's left over after we've taken a proton off the water. So of course, products of reactants raised to their coefficients includes the conjugate acid of the base times the molarity of the hydroxide over the molarity of the base itself. If there are coefficients, they'd be in the exponents. Probably that's not going to happen, and the liquid water is not included. Okay. Number 4 says, who knows the conjugate base for acetic acid? Okay. Acetic acid can either be written as HC2H3O2 or CH3COOH. If you add up all the carbons, hydrogens, and oxygens, you'll see they're the same thing. When they act like a weak acid, they lose an H+, and the conjugate base is the acetate ion. So it's this, C2H3O2 with a negative charge, or CH3COO with a negative charge. Either way of writing the acetate ion, that is the conjugate base for acetic acid. Okay, number 5. Someone who knows that a buffer must have both a weak acid and its conjugate base. Of course, that comes from the definition above. Now, both forms of the titration equation, you learned this last year. But now you know that you can take either side of this and set it equal to moles. So it could be MbVb equals moles of H plus or moles of OH minus. It could be MaVa equals either of those. When you do this, your volume needs to be in liters so that it will cancel out with the liters in molarity. Okay. Let's see, we are at this one. Can draw a titration curve for a strong acid and weak base. In this case, the weak base will be in the flask. The strong acid will be in the Burette. The strong one is always in the Burette. So if the weak base is in the flask, we start at a high pH, but it's weak, so it's going to fight a rapid change in pH. So this is the buffering action right here. And then it will hit the equivalence point and then flatten out. The equivalence point will be less than 7. It'll be a little bit acidic because you have a weak base. When your weak base has been fully neutralized, you have its conjugate acid in the solution, and its conjugate acid will make this a little bit acidic, at least just a little bit. Okay. The Henderson-Hasselbalch equation is, of course, right here. It is either of these, pH equals pKa log and so on, or this one with the pOH if you have a base, And if you need to use this one and you want to know the pH, you of course find the pOH and subtract it from 14 and you'll have the pH. The equivalence point is the place where all of the acid or base has been fully neutralized. It's also good to know the half equivalence point. The half equivalence point is where your molarity of weak acid equals your molarity of conjugate base, or vice versa. Okay, for this guy, Ka and Kb are mathematically related using Kw. Ka times Kb equals Kw, which is 1 times 10 to the negative 14. So if you know Kb for a base, you can take this guy, divide it by the Kb, and find the Ka for its conjugate acid. Or if you have a weak acid and you know his Ka, you can do the similar thing to find the K for the conjugate base. Okay, we're right here. A buffer solution resists change in pH through its ability to combine with both hydrogen and hydroxide ions. Okay, a Ka expression is, of course, this guy, hydrogen ion molarity times conjugate base over the weak acid molarity. Okay. Titration curve for a weak acid and a strong base. Okay. It would be the flip of this. We would start at a low pH because we have a weak acid in the flask. It would have buffering area where it resists the change in pH, and then it would shoot up and flatten out as we add strong base. The equivalence point would be greater than 7. Because it's a weak acid, when the weak acid is fully neutralized, we have its conjugate base floating around in solution. Its conjugate base will make this a little bit basic. Okay. Amphiprotic means something that could be an acid or a base. A good example would be HSO4-. I just took sulfuric acid and took one of his hydrogens off. So he could act like an acid by giving away his second hydrogen, or he could act like a base by taking back his first hydrogen. Water is another great example. He can give away his H+ and be hydroxide, acting like an acid in that case, or he can take an H+ and become hydronium. Okay, an indicator that is good for titrating a weak acid with a strong base. Gotta go with phenolphthalein. Let's see. Here's why. Weak acid, strong base, your equivalence point is going to be a little bit greater than 7. Phenolphthalein changes from 8 to 9, and he just barely starts to change at 8. So that's why he's good, because your equivalence point is not actually at 7. It's a little bit greater than 7. Okay. Finally, the conjugate acid for ammonia. Make ammonia act like a base, make him accept a proton. After he has done that, he will be the ammonium ion, and now he is the conjugate acid for ammonia, NH3.